Hi, Assalamualaikum. Welcome back to our online class. So today we are going to learn a new thing in continuation with the previous topic that we have covered last week. So we had learned on how to read the IR frequencies. We understood that from the frequencies we can tell how strong the bond is. This is actually started with the nuclear charge. So we have compared the nuclear charge against the number of electrons in the given molecules, and we found that when the nuclear charge is greater than the number of electrons, the degree of pi bonding from metal to carbonyl will be lower, and electron density consequently definitely will be lower because there are no electrons moving from metal to your LUMO. What happened to the bond order? It will be higher, and this will increase the strength of the bond of your carbonyl. Hence, the frequency of your carbonyl will be automatically higher, and the bond length will be shorter. So the shorter the bond length, the stronger it is, and this can be seen from the higher frequencies on the IR spectrum. The same thing, the opposite thing happens for vanadium. In this case, you can see that the number of electrons outweigh the number of your proton. So in this case, the degree of pi bonding will be higher because they are loosely held, and then consequently the electron density in the LUMO will be higher because there are more electrons coming from metal to your LUMO, and the bond order would be lower. Consequently, the bond strength would be lower, and definitely your bond strength would be lower, and your bond length would be longer. The longer the bond length, the weaker it is. So this can be seen from the IR frequencies. Lower IR frequencies for vanadium, which can be seen from these values. Okay, so manganese 2090 and your vanadium 1859. So slightly lower than manganese because there is a higher likelihood for the back bonding to happen, hence making the bond strength weaker, and this can be translated in the IR frequencies. I hope you do understand this because this is the fundamental part of the topic. So I hope you can master this. If you don't, do not hesitate to ask me in the WhatsApp group. Now moving on, we're going to learn IR again, but this time around on alkane bonding. So we have learned about olefin. So olefin consists of C double bond C bond in the structure. So we want to see the effects of this bond on the spectrum. Now, effects on C double bond C. The first one is we are going to see the sigma donation. This is the first step. Remember, we have two steps needed to be taken in order to form the complex. One is sigma donation, where the pi electrons are coming from your HOMO to your metal, and the second step would be the pi back donation, where metal is giving back the electrons to your LUMO, which is pi anti-bonding. Now, what would happen? The net effect of these two processes would be both will lower the single bond C bond order, will lower the bond order. Remember just now, when I say the bond order is lower, the bond strength also lower, but the bond length would be longer. So the longer the bond length, the weaker it is because the bond order is now lower. So from that understanding, we can predict that weaker and longer CC bond, because the net effect of these two processes will make your CC bond order lower, and then the bond strength would be lower, and the bond length will be longer. So weaker and longer CC bond. So from the experimental evidence shows that the C double bond C, the C double bond C is weakened upon complexation. So meaning when we compare the free alkene with the bonded one, we can tell that it is weakened upon composition. How do we know? Because the free ethene has a bond length around 1.34 angstrom. But when it is complexed with a metal, the bond length now become 1.38, slightly longer. So this means that the bond is now weaker, and of course this will be translated in the stretching frequencies on the IR spectra. You can see that the free ethene will be around 1,623, but for the complex in the zinc salts it is 1,516, drastically reduced. The frequency reduced from free ethene to the complex because the bond length is now longer. Why it is longer? Because it is now getting weaker. Why it is weaker? Because the bond order is now lower. So that's how you relate from bond order to bond strength to bond length. Okay, I hope you are clear with this one. Now, structural characterization of organometallic compounds. Again, this is on DIR spectroscopy. There are actually three main characterizations that we can carry out in order to characterize your organometallic compounds. It can be done through IR, infrared spectroscopy, or carbon-13 NMR spectroscopy, or proton NMR spectroscopy. But we are going to be focusing on the first two, which is your IR and carbon-13 only in this syllabus, because the proton NMR, I'm sure it has been well covered in other organic chemistry courses. Now look at this. We have terminal carbonyl will be having higher frequency comparatively against your bridging carbonyl. Now the position of carbonyl bands can provide important clues to the electronic environment of the metal. Electronic environment means how dense the electron is there. Okay, if it is high in density, we call it rich in electrons, and if it is not that dense, then we call it lower electron density. Okay, I hope you are familiar with these terms. The greater the electron density on the metal, the greater the degree of pi bonding. Definitely, because as I said, metal is electropositive by nature, so it has a higher tendency to be giving back the electrons. Whatever electrons that they are obtaining from the. So when that happens, I mean, when the greater the degree of pi bonding, due to the excessive electrons that your metal is holding. So when that happens, this corresponds to the lowering of your bond strength, definitely, because the higher the degree of pi bonding, the weaker the bond is. And this, of course, will lower the bond order and will make the bond length longer. So this can be seen from the frequencies of your IR. So it will be much lower. So compounds with more than one carbonyl ligand usually have more than one IR active carbonyl stretch. So definitely when you have more than one carbonyl, you should be expecting more band of your CO on the spectra. We are going to learn this later in the following table. So each stretching frequency corresponds to a linear combination of stretching and compression of carbonyl bonds. So it will be a little bit complicated, but we are going to focus on few important parts of the structure. Now let us move on. So this is infrared active modes for some carbonyl complexes. We take this one example. We have hexacarbonyl. This is the structure. This octahedral. We are expecting one frequency of your carbonyl. Okay, it depends on the symmetry, so it depends also on the point group. it is not covered in the syllabus, but the important part of this table would be what would happen to the number of frequencies expected when you are given with the certain structure. So for example, the second one we have 5 CO, this is pentacarbonyl, and with 1 L. L means ligand, another type of ligand other than your carbonyl. So when it happens, we should be expecting 2 or 3 significant band appearing on your spectrum. So we have A1 plus E plus A1. So the total is 3. This one symmetry is 1. So that's why we expect 1 band only. And then moving on. Now number 3 is, I would say, the most crucial part. You have to understand the structure of trans. You see trans here. These two on the opposite side, and this says they are situated or located next to one another. So this is the structure of trans, and this is the structure of cis. You might be given the structure of trans and cis, and you will be required to differentiate these two compounds. How do you do that? It depends on the number of stretching frequencies on your IR spectra. Like for this one, you can see for trans, normally you will appear as 1 stretching frequencies, but for cis, normally you will be expecting 3 or 4 stretching frequencies. Okay, so please focus more on this particular part. Number 4, we have mer and phase. This is your first task today. Can you find the meaning of mer and phase? These are also examples of your isomer. So for mer we expect 3, and for facial we expect 2. Okay. For the rest you can see and read, like we have axial and equatorial. This is your second task today. What do you understand by axial and equatorial? I'm sure since you are in your final semester, you have learned this axial and equatorial in some other courses. Can you tell me what are mer and facial, and then what would be axial and equatorial isomers? Okay. So for axial, we expect 3 frequencies. For equatorial, we expect 4 frequencies. Moving on, we have some other types of ligand here where you can read on. When we have 5 ligands, 2 of them is carbonyl and 3 of them is some other ligands, you should be expecting 1 or 2 frequencies. If you have 4 carbonyl ligands, you should be expecting only 1 stretching frequency. Now, this is how your spectra will look like. Now, for the first one, we have A1, B1, and B2. How many stretching frequencies here? 3. So you have 3. So from these, can you guess what kind of geometry that they're going to have? How the atoms are going to be arranged in that particular molecule? Can you tell us? So it depends. Yeah, it can be MCO3L2 with 3 frequencies, or it can be your axial MCO4L 3 frequencies, or it can be your MCO3L3 mer with 3 frequencies, or it can be your MCO4L2 cis with 3 frequencies, or it can be MCO5L 2 or 3 frequencies. So you will be given with the chemical formula, so you can always figure out based on the frequencies appeared on your spectrum. The same thing for this one, we have 1, 2, 3 frequencies. So for these 3 frequencies, you see, this is actually the infrared spectra of the geometric isomers of molybdenum. We have CO4 and then POPH3. This is phosphine complexes. Sorry, I can't really see it clearly here. With 2 phosphine here. So it is actually MOCO4L2. 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 Let's see this one. MCO4L2. But we see 3 frequencies. So it cannot be trans. So it must be cis. So the structure is cis. Okay, because we should be expecting 3 or 4 frequencies. Now, in carbonyl complexes, the number of carbonyl stretching bands cannot exceed the actual number of carbonyl ligands. Meaning, if you have 4 carbonyl, you cannot have 5 stretching frequencies in spectra. If you have 2 carbonyl, you cannot have 3 stretching frequencies on the spectra. But there will be cases where you can get it, okay, where the vibrational modes are not IR active. So I hope you do understand that to be IR active, your compound should be having a polar bond. The functional group itself must be polar, and in order to be polar, it must be having a dipole moment. But there will be cases where for example, if it is symmetrical, the dipole moment can be cancelled out, so you could not see it clearly. So it can be the reverse more carbonyl groups are seen than the IR bands, meaning sometimes they can have 4 carbonyl, but you cannot have the significant number of bands on your IR spectra. Okay, moving on. Complexes containing 3 or more carbonyl generally exhibit different numbers of carbonyl bands, okay, which can be predicted according to symmetric approach. So, as I said, the more symmetrical it is, the less number of carbonyl stretching frequencies you can see on the spectra, because we count them as 1. It works just like your NMR when it is having the same numbering atoms, or when it is symmetrical, so we don't count every single proton that we have in the structure. Normally we just sum it up as one signal. The same thing for your carbonyl here. If it is symmetrical, the more symmetrical it is, the less number of carbonyl can be seen. For example, you look at this one, like this one. This is symmetrical, right? Very symmetrical. That's why you see only one signal or one band only on your spectra. Although we can use IR band to tell the structure to characterize our organometallic compounds, but there are cases where we might have some problems. Okay, bands may overlap to such a degree as to be indistinguishable. So even though we are expecting 3 stretching frequencies, for example, on the spectra, but sometimes these bands can be overlapping. So it will be difficult for us to tell how many frequencies that we have. So consequently, we cannot tell whether it is cis or trans, and so on and so forth. So one or more bands may be of very low intensity and not readily observed. So the second one is in terms of intensity. If it's not polar enough, so the intensity of the peak will be very much lower. So it will be difficult for us to tell whether this is the peak or this is not the peak. Okay, but despite all these, normally we can always do the characterization for our organometallic compounds. We're going to move on to the last part, the last subtopic of our lecture today, which is on the carbon-13 nuclear magnetic resonance spectroscopy, or carbon-13 NMR spectroscopy. I'm sure you are very, very familiar with this spectroscopic technique. Nothing much to be discussed on here, and I hope you are familiar with the facts of carbon-13. So shown in the table here are the chemical shift for certain carbonyl. Normally will appear around 177 to 275. You can see metal to olefin, normally 3 to 100 ppm. And then you can see also for for phenyl here, it can be 131 to 193, depends. So we have auto, meta, and para here. So different position will give you different reading, different chemical shift. Like for auto is 132 to 142, for meta is 127 2131, and for para it is 1212131. I do not intend to elaborate further on this because I assume that everyone knows what ortho, meta, and para are. Now look at this. We have one example with the formula Cr, chromium is the metal, with this one ligand and 5 carbonyl. It is actually MCO5L. So the IR and the carbonyl, we are expecting 3 stretching frequencies here, 2057, 1980, and 1908. And the carbon 13 give you 216 and 223. So how do you explain these observations? Definitely we have 5CO and then 1 other ligand. Also we are expecting octahedral geometry here, as you can see here. Easy. So this is, as I said, this is metal with 5 carbonyl and 1 ligand. So expected there are 2 or 3 IR bands. This agrees with the 3 stretches that we expected earlier in the table. So there are 2 types of carbonyl, equatorial and axial, which can be assigned to carbon 13, 216 and 223. So can you tell me, again, this is the question that I asked earlier. What do you understand by the term equatorial and axial, especially when this kind of chemical structure is given? So I'm going to stop here, and we're going to continue with some other subtopics later in the another video. Thank you very much for your kind attention.